Our next speaker is David Burkhalter. David is from the Department of Civil, Construction, and Environmental Engineering. The title of his talk is Building Better Bridges.
Basically, we have developed a new bridge girder, like a beam, that's longer and it's stronger and it prevents a certain type of cracking. So my thesis is on developing that girder, designing it, and then we're also testing it in our labs on campus.
Very cool. And then just one more question, if you don't mind telling me a little bit about how you're feeling today going into the competition.
A little nervous, but I've practiced this thing like 600 times, so I feel like there's not much else I can do. So I told my friend to stand by the fire alarm in case something happens. Just pull it. If I start messing up, just pull it and everybody has to leave. So that's my plan. I know what you may be thinking. Building better bridges? We've been building bridges for thousands of years. What can we possibly do to change the way that we've been designing them? And if there is something, then how come we haven't done it yet? Well, to answer this question, let me first bring your attention to some bridge anatomy. Bridges are comprised of four main structural elements: foundations, piers, girders, and decks. Now today, we're going to talk about bridge girders. Bridge girders are just the beams that transmit the load from the moving cars above to the foundations below. In bridges today, many designers use pre-stressed concrete girders. Now, pre-stressed concrete is just like normal concrete on the outside, but on the inside, it has a special steel strand that runs from one end to the other, bonding with the concrete and making it much, much stronger than normal concrete. To illustrate the strength of pre-stressed concrete, think about it this way. Imagine you have a girder that's made of plain concrete. You then loaded this girder with the weight of a moving vehicle, or in our case, a Big Al mascot. Well, that girder would ultimately crush under the weight of Big Al. Well, say you took a second girder and you added reinforcing steel on the inside, or rebar. That girder would be much stronger, but still would deform and crack under the weight of Big Al. Now, say you took a third girder and you added a pre-stressing strand on the inside of it. This strand would bond with the concrete and pull the ends together in compression, making it much stronger. Now, this is the concept of pre-stressed concrete, and this is the principle that engineers today are using to design girders. In fact, they're using this principle to design longer and longer bridge spans. But in order to reach these long spans, they have to add more and more pre-stressing strands on the inside. And this huge amount of pre-stressing strands on the inside of the girders is creating a huge amount of force on the inside of the girders, which is ultimately cracking the ends of the girders. Now, this is our problem. We call it end zone cracking. And end zone cracking is bad because if you've ever left a garden tool out in the backyard before, you know the detrimental effects that rain can have on steel. And when that steel is suspended in air, holding millions of pounds and thousands of lives, we don't want to take any chances on the rain getting through the cracks and into the steel. So, this is where my team comes in. We've developed a new girder, a really big one, that can span 180 feet long. It can hold 66 pre-stressing strands, and it can hold up to nearly 3 million pounds of pre-stressing force. Through the strategic placement of the steel on the inside and the addition of a debonding element, we've been able to create a girder that's much stronger and can prevent end zone cracking on the inside. And now we've taken this girder and fabricated it and brought it to our labs for testing to verify our design. As a result, we have a better girder, and it will ultimately give us better bridges. Thank you.